Another situation, reduce problem size by half. Cut in half. Reduce the problem size by half. Okay? So this case, many problems, we have this case. So let's look at this special. Yes, that's also. Yeah, so later we have that divide and conquer, right? Divide and conquer. We divide in half. Right in the middle, then we conquer. Yeah. So this one has that similar idea. Divide and conquer. Divide in half. Okay? Reduce problem size by half. Okay. All right. Let's look at the problem first. Count binary digits. The problem is not that hard. Count binary digits. Okay? And the bits. Binary digits we also call bits. Okay? Yeah. Binary digits, bits, number of bits. Okay? Given a positive decimal integer n, we want to convert it to a binary number. After the conversion, you need to count how many bits do we have for that binary expression. That's the problem. That's the problem. Count binary digits. Okay? Yeah. Find the number of binary digits in its binary representation. Okay. Yeah. So that's a simple problem. Okay. All right. But we need to review what is the binary representation. Okay. So you'll learn this in discrete math. Also discrete math, binary representation, right? Chapter 2. Okay? Yeah, I remember. So, yeah, because I was a substitute teacher for that part, binary representation. Okay? Yeah, once in summer. Yeah. All right. The binary representation, you write n in this way. Okay? Yeah. The base is 2. The base, you use 2 as the base. So then based on the position, all your bits, 1 or 0, only 1 or 0. But the highest bit cannot be 0. Okay? The highest bit has to be 1. Okay? Otherwise, you do not count that term. You go to the next term. Okay? Yeah. So that's the binary representation. Okay? We want to count. When we do this conversion, how many B digits, right? Yeah, also digits, B digits do we have? Okay? We need to find that S. If we can find the highest bit, S plus 1 is the answer. Yeah? Because this B0, okay? BS, B0, we have S plus 1 bits. That's the answer. But we need to have that S. Then S plus 1 is the answer. Okay? All right. The method. How do we do it? How do we get the highest bit? Okay? Yeah. All right. Method. Okay? Yeah. So look at highest bit. Okay? All right. Base 2, we need to use that property. Factor base 2. Okay? Yeah. Look at this. Division by 2. Here, if we use division by 2, we can get to the highest bit. Division by 2. Okay? All these terms, we can eliminate them. Okay? One by one. Okay? All right. The first time, let's do division by 2 and then take the floor function. How about that? Divided by 2, n over 2. Other than the first one, each term is a multiple of 2. So we can do division. No problem. But this one, when we take floor function, it's gone. Right? When we take floor function, it is gone. See? Okay? But if we do another division by 2, take flow function, B1 is gone. Right? Another division by 2, flow function, B2 is gone. Okay? Gone, gone, gone. At the end, BS is left. Right? Yeah. Let's just count how many divisions do we do. Right? Count that number. So we get that S. So we get that solution. Yeah. Right? So that's the method. Reduction. Every time we reduce the problem size by 2, see? Divided by 2. This is our problem size. After one reduction, this is our new problem size, approximately 1/2. Another division, approximately another half. Okay? So on. Okay? Yeah. So division by reduction by half size. Okay? Yeah. Now let's look at that using the recursion idea. Recursion. Recurrence relation. What do we get? Recurrence relation. Okay? Yeah. For the original problem, let's assume this is the binary recur of n. That's the original problem. Okay? Now, we do the division by 2, flow function. Okay? This is a new problem size. New problem size, how many bits do we use? Okay? So this function gives us the number of bits for n. Now, after this division, we get a similar problem, same problem, but for smaller size. The size is flow function n over 2. Okay? So we still call the same function, recursive call, but the difference of number of bits is 1, right? 1 bit different. B0, you don't have B0, you have B0. So the difference is 1. So that's why we have this recurrence relation. Okay? Yeah. All right. So now the question. So we derive this recurrence relation. Pretty simple. Yeah. But in order to find its solution, there is a difficult part. You just look at this whole formula, okay? Look at this whole formula. Which part you feel the hardest? Which part you feel the hardest to handle? So if I ask you to work on it, you feel this part is the hardest. Can you tell me which part is the hardest? Other students? Any place you feel, if I work on it, I don't know how to deal with it. Is there such thing? Somewhere you feel not quite right. I don't like to see this. Is there things like that? Flow function. Flow function give us a lot of problem. We don't know how to deal with it. Flow function. Okay? The hardest part. All right. So let's try to solve it. Okay? So the biggest difficulty we want to overcome is this flow function. Is that flow function. Okay. Yeah. How to get around it? We want to get around it first. We want to get around it. To get around it, can we make some assumption to avoid it? If n is an even number, do we have that flow function? No, we don't have it. Okay? So sometimes we can make some assumption to make our life easier. Okay? So we assume n is an even number. But if n is an even number, the next one, when you call recursion, you will get another flow function, right? So sooner or later, you will get trouble, right? Yeah. Now, can we assume n is power of 2? If n is a power of 2, we never have that flow function problem, right? we can do division by 2 all the way without any remainder. Okay? So our first assumption, let's assume n equals power of 2. So we solve this problem under assumption n is power of 2. After that, then let's look at the general n. That's not general. N is power 2. It's not general. But after we solve that power of 2 case, then let's go to the general. Yeah. Because we already have the power 2 solution. Now, we hope when we go to the general case, it should be easier. Okay. All right. So we run out of time. So next time, let's solve this problem. Okay. Solve it.